Okay, I guess while that's loading up, I can just take you through an outline of the talk today. So we'll start talking about sequences, what they are, and how we can model them. Then we'll look at applying some of the deep learning techniques you've learned earlier in the week, like specifically feedforward networks to the problem of sequence modeling. And we'll see that there's some limitations with that approach. It's like, it'll work, but there's some limitations. And we'll use those limitations to motivate the introduction of recurrent neural networks, which are designed specifically for modeling sequences. So with recurrent neural networks, we'll look at how to train them using an algorithm called backpropagation through time. And then we'll look at some examples, and also address some of the issues with training recurrent neural networks, which motivated the introduction of so-called gated recurrent neural networks, which include the LSTM and GRU, which you may have heard of. They're very popular architectures. And finally, if we have some time left over at the end, I'll very briefly introduce attention. So now I'll just wait for my slides to come back. All right, so we talked about the outline. Let's jump straight into sequences and what they are. So sequences are really just observations of some data. But the important thing that distinguishes sequences from just a bucket of data is that the order of elements in a sequence matters. So for example, if you think about a phrase like dog bites man, and another phrase, man bites dog, those are exactly the same words, but because they occur in a different order, the meaning is completely different. So sequences occur kind of all around us in the real world. So some examples might be written text. So you can look at text, like we just motivated, order in text matters, whether it's the order of characters in the word or words in a sentence. There's lots of examples, say in healthcare, maybe signals from a heart rate monitor you can think of as a sequence of observations. In particular, those are time series. A time series is just a sequence where it's ordered by time. Other examples from healthcare might be like electronic patient records or admission history of patients in a hospital. Amazon, for example, might use sequences to model your history of purchasing items, to use it to suggest what you might like to buy next. Finance, of course, is full of time series, so sequences ordered by time, like, for example, the share price. Every day you might observe a different share price, and you can model that as a time series. DNA, we heard about yesterday, is a sequence which you can represent with these 4 letters, A, G, C, and T. And the order of those letters determines the function of the DNA. Weather could also be seen as a sequence, so the weather yesterday or the day before and over the weekend maybe you can consider that to be a sequence of weather patterns. So the tasks we might want to perform with sequence data include sequence prediction. So we might say Saturday, Sunday, Monday, and Tuesday were all sunny, and so therefore we want to predict that maybe tomorrow is going to be sunny. Another task you might want to perform is sequence classification, which is where we have a sequence of data and we want to label that sequence. So maybe if you have a Google Assistant device that has a microphone and it listens to some audio, and that audio is a sequence. And it then might want to determine whether you said, OK, Google, or something else. The third thing we might want to do is sequence generation. So suppose we might want to have a model that can create new music, or can create new text, or can translate text from one language into another, or maybe take in an image of a dog and generate a caption for it, saying, the dog ate my homework, for example. So to introduce some notation that we're going to use for the rest of this talk, we talk about a sequence as a list of some observations, and sorry. Let me see. Can you see this pointer? Probably not. Can? Okay. So a sequence is a list of observations which we denote as X, and we put a subscript on these X's to indicate the position in the sequence. So X2 occurs in the second position of this sequence. Okay. Now the sequence prediction task we can say is the task of modeling the probability distribution of the next observation we might see given the set of previous observations we have seen. So you can think about this as sort of processing a sequence left to right, or maybe processing it online. So up to today, say we've observed the weather was sunny, 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 and it's sunny today, and now we want to ask ourselves the question, what is the weather going to be like tomorrow? Maybe you'll say there's an 80% chance it's going to be sunny, and a 20% chance it'll be raining. And then tomorrow, we will now be at step x t plus 1. We will observe what the weather is tomorrow and use that to refine our model. Okay, so there's some problems we need to be wary of when thinking about sequence prediction like this. So the length of our sequences could get very long, right? Maybe weather has been going on for thousands of years, right? So do you track the weather for so many centuries in your sequence modeling? Like, that's not really practical, right? Also, that creates modeling issues because the condition on your probability distribution changes every time. So every day you'll have one more observation, and now you have an extra conditioning variable. So practically what people do is that they would either truncate the history to some fixed length. So in this example here, we're going to say that the probability distribution of our next observation, given the history in our sequence, is approximately equal to the distribution only conditioned on the last few elements. So here we just call it tau, so tau elements. So we might say, okay, we're only going to predict our weather based on the last 5 days of observations. Now, if the sequence we're modeling obeys the so-called Markov property, then this is actually a good approximation. In fact, it becomes exact. But most sequences in real life don't obey this Markov property. So another technique we could do is we could introduce a new variable, h, and we call this a latent or hidden variable. And the purpose of this variable is basically to keep a running summary of the entire history of our sequence. So one thing you could do, for example, is just like literally concatenate every single observation into this h, and then this would be an equality rather than approximation. But more practically, this h is going to be some compressed representation of the history of our sequence. So every time we make a prediction using our sequence, we will update our latent variable to capture the most recently observed information. Okay, the sequence classification task we can view as a probability distribution over some target y. So this could be, did the person say, okay, Google, or something else, given a sequence. So this could be like the representation of the audio wave that was picked up by the microphone. The sequence generation task is equivalent to modeling a joint distribution over an entire sequence. And we could condition this on some other information. So when you're doing image captioning, for example, you might run a convolutional network on an image and come up with a representation of that image, which we call C, and then model a joint distribution of the sequence of words describing that image, conditional on the representation of the image. Now, one thing you can do with probability theory is you can factorize joint distributions. So this distribution here, this joint distribution over the entire sequence, can be written as a product of conditional distributions. So the joint distribution of the sequence x1 to xt is the probability of x1 times the probability of x2 given x1 times the probability of x3 given x2 and x1, and so on. And this applies to any distribution. This is just a general law of probability. But this thing hopefully looks familiar, right? This is just what we were trying to model when we were doing sequence prediction. So this means that we can think of sequence generation as essentially the same as doing sequence prediction. And we call this autoregressive modeling because we're trying to do a regression of a variable x on its own history. Okay, so as a quick digression, when talking about time series in particular, you'll often come across this concept of stationarity. So stationarity is actually a very desirable property in sequences. It makes them a lot easier to model. And what it means is that the statistical properties of the sequence don't change over time. So some statistical properties might be the mean or the variance of the distribution. So a stationary sequence has the same mean across all time and the same variance across all time, whereas a non-stationary one, those things change. So this picture on top here is a picture of a share price. On the x-axis is time, and on the y-axis is the share price. So maybe let's give a quick show of hands. Who thinks that this sequence is stationary? One person, cool. And who thinks it's non-stationary? Excellent, cool. So you understand the concept. This is non-stationary because suppose you chop this sequence in half and you compute the average of the first half and the average of the second half. So the average of the first half is probably around here somewhere, and the average of the second half is up here. So the mean changes over time, so it's non-stationary. Also, in share prices, you'll find the variance changes, quite, like, for example, in a market crash, the variance will increase substantially, although it's a bit hard to see that in this picture. Okay, so I don't need to ask you about the second one. I'm sure you know that that is stationary because the variance is the same and the mean is the same. It's just 0. I know this is stationary because it's just standard Gaussian noise. Okay, as another example of a sequence, here's a noisy sine wave. So this is just a sine function with some Gaussian noise applied to it, and the code to generate it in NumPy. So here, really what I wanted to show you is just what a sequence looks like. It's just some observations, so some data points, and each of those data points we assign a label depending on its position. So this first one is x1, then x2, x3, and so on. Okay, but that was a nice, easy example because it was just scalar values. But in real life, we'll usually be working with more complicated looking data. So let's look at the DNA sequence, for example. So we know we have these letters, A, G, C, and T, and this forms our vocabulary. But most machine learning models take numbers as input, right? Not letters. So how do we convert this into numbers? So one thing you could do is you could just assign like numbers 1, 2, 3, and 4 to A, G, C, and T. And this will work, but probably not very well. So instead, what people do is they generally use one of two techniques, which we call encodings. The first one is a so-called one-hot encoding. So this is based on a similar idea to the assigning a number to each of these letters. So we'll say A is 1, G is 2, C is 3, T is 4. But instead of just using those numbers as input to our model, instead we'll construct a 4-dimensional vector which has zeros everywhere except for 1 in the position corresponding to the index of that letter. So A gets a 1 in the first position, G gets a 1 in the second position, C gets a 1 in the third position, and T gets 1 in the fourth position. Okay, and now if we have a sequence like GGCTA, we can represent this. We can basically just substitute the appropriate one-hot vector for each of the letters and construct our encoded or embedded sequence like this. Okay. The other technique people use, because imagine now you're trying to model like English text, and you're trying to model words in English text. Like there's hundreds of thousands of words in English, right? So maybe you come up with a vocabulary of 100,000 words, but now you're going to have vectors that are of length 100,000 with 99,999 zeros in each vector and just a single one. So that's very inefficient. So what people tend to do in those scenarios is use so-called dense or distributed encodings. So these would be shorter vectors of real numbers that look something like the example here. Now, the nice thing you can do with these dense encodings is you can actually add more information into the encoding. So this is a very common trick used in NLP. Like you may have heard of word-to-vec or glove embeddings. So what they do here is they actually incorporate information about sort of words that tend to occur frequently with other words into their embeddings. And basically, they end up with vectors that have this nice property that words that have similar meaning, say are synonyms for each other, have vectors that are close together in Euclidean distance. So this actually gives our models more information built into the inputs. Okay, so looking at this in code again. So here, I've just done a mapping. So this is just a Python dictionary that maps my 4 letters into one-hot vectors. So because there's only 4, I just hard-coded it. But NumPy and TensorFlow and stuff have functions that can do this. Now, if I want to encode the sequence of DNA, all I do is I map each letter to the appropriate one-hot vector, and I end up with a list that looks like this. So now we just have a list of vectors represented in NumPy. Okay. Now suppose I want to do some fixed length autoregressive modeling. What I'd need to do is split these into subsequences, shorter subsequences. So because I have a fixed context length, say it's only 4, I may want to split these into groups of 4. So that's what the code on the right here does. It just, you'll see in the output that we now have groups of 4 vectors. And we can model each of these separately. Okay. So now that we know what sequences look like, let's try and apply a deep learning technique that we've learned about earlier this week. So specifically the feedforward network. So feedforward networks don't take sequences as input, right? They take a single vector as input. So one way we could address this is we could say, okay, let's assume we're just doing fixed context length modeling. So we're only looking at the last 3 observations in our sequence. What we could do is we could just take the vectors for the last 3 observations and concatenate them on top of each other to create one long vector of 12 elements. And we can pass that into our feedforward network, maybe through some linear layers, end up with a 4-dimensional vector. And this 4-dimensional vector you'll see being referred to as logits, which are like unnormalized probability distributions. We can apply a softmax function to convert that into a probability distribution. And now, for example, this feedforward network is saying the next observation is not very likely to be an A, quite likely to be a G, somewhat likely to be a C, and maybe not likely to be a T. Now, in order to assess how good that prediction was, we need to compare it to a target using a loss function. So here we just use the cross-entropy loss, and then we use backpropagation to update the weights of the feedforward network so that it improves its predictions the next time it sees such an example. So yeah, I went through that very quickly because hopefully this is just a recap for you. Okay, so feedforward models are usually a very good place to start when doing sequence modeling. They actually, in practice, tend to perform quite well, but they have some problems. So imagine we're processing our sequence in an online fashion, so like left to right through the sequence. And suppose we're only on the 2nd day of recording observations, and we only have the previous day for context. Now, our previous example, we said we needed 3 vectors to be our context. So what do we do if we only have 1? Well, we could just say our model's not going to work until the 4th day, or we could fill in the missing values with zeros. But in order to do that, we'd have to make sure that when we train our model, it's got enough examples of having zeros in those extra places. We also might have a problem with what if weather is very seasonal and the observation from 1 year ago is actually very influential on the weather pattern, on the weather prediction for tomorrow. So this is a long-term dependency. So if we have a fixed context length of only 5 days, how do we capture that there was relevant information a year ago for the prediction we need to make today? another problem is that MLPs or feedforward networks will have separate parameters for each position and no sharing of information between positions. So if we have these two sentences, I went to Kenya in 2019 versus in 2019 I went to Kenya, like these mean the same thing, and the 2019s here are the same, but the MLP will have separate weights for 2019 in the 6th position and 2019 in the 2nd position, and no way really of exchanging information that those are the same thing. So we need an architecture that can support sharing of parameters across time and also supports variable context length. Well, we know how to support variable context lengths already because we looked at this latent autoregressive modeling earlier. So the idea is that we introduce this latent variable that summarizes the entire history of observations that we've seen so far. So this H could contain information from the last year or 2 years or 3 years of weather, however many observations we've done. And remember then, we update the latent state to include current information. Okay, so what a recurrent neural network looks like in pictures is here we have an input, so this is our observation. So this would be, for example, today's observation. And we have a previous latent state. So this would be the state that was carried over from yesterday, and that keeps track of the history of weather. Okay? The output of the recurrent neural network cell is an output, so this might be a prediction for tomorrow's weather, and an updated state, so incorporating today's information into the state for future predictions. Then, once we get to tomorrow, we just run this again in a loop. So this is what this dashed arrow here represents. So today's updated state becomes the previous state for tomorrow. And we keep doing that in a loop. Okay, what happens inside this cell? Well, there's really just two simple equations. So we have two weight matrices, so WHX and WHH. We use those weight matrices to multiply the input and the previous hidden state. We add them together, we add a bias, and then we apply a nonlinear activation function. And this is how we incorporate current information into our new latent state. Then we apply another affine transformation, or linear layer, if you will, to convert this updated state into an output. So you'll notice here that this HT-1, that would have been computed yesterday using yesterday's observation and HT-2, which in turn would have been computed using HT-3. So what we've defined here is a recurrence relation. And this is where RNNs get their name from. So just in pictures, this is what these equations look like. I'll skip that because I went through it pretty slowly anyway. In code, this is what it might look like. So suppose we have a model where we want to have a 5-dimensional hidden state vector. We have some 4-dimensional input, like the one-hot vectors from our DNA example. And we want an output that is a 4-dimensional vector. So the probabilities for each of the 4 letters. Okay, we initialize our parameters. So here are the 3 weight matrices. So WHH, remember, maps from HT-1, which has size hidden size, to hidden size. WHX maps inputs, which have size input size, to hidden size, so that because we need to add them together. And the bias, BH, has size hidden size as well. Okay? WOH takes, remember, WOH takes the hidden state, which has size hidden size, and maps it to the output size. So that's why its shape is output size by hidden size. Okay? We define an RNN cell, which takes as input the current observation and the previous latent state, and uses NumPy's dot function to do the matrix multiplication. It returns its outputs, the updated state and the current output. And then we can loop over our embedded sequence or our encoded sequence, each time passing in. So now we're looping through our sequence left to right, and each time we pass in the current observation and the previous state, and we update the state and collect the current output. So this is what the outputs look like. So this looks like gibberish at the moment because this is just a randomly initialized RNN. We haven't trained it, but we'll get to training in a bit. Okay, just some things to talk about before we get to training. Suppose we know the length of the sequence. So we already done 10 observations, and we know our sequence length is 10. What we can do is we can actually unroll the recurrence. So we can actually run the recurrence 10 times, and visually we can represent the RNN as in this picture. So we have 4, say our sequence length was 4, we have 4 cells next to each other, each taking in one of the inputs. And we can now treat this essentially as a feedforward network, where these cells might be your layers in the feedforward network, and it's processing left to right. So perhaps then you could use your standard optimization techniques to optimize this. But the one thing we just need to be careful about is that unlike a feedforward network, where each layer would have its own weights, in an RNN, these weights are shared. Because remember, RNNs do weight sharing across time. So here we just collected up the weights into this symbol omega here. And it's the same omega that's used in every one of these cells. So that causes a little bit of complication. Okay, since we're at the deep learning Indaba, and we're doing deep learning, not shallow learning, we want to make deep RNNs. So in order to do that, we can just take these same RNN layers that we've defined and just stack them one on top of each other. So on the left, we have our input goes into an RNN cell, and the output of that cell becomes the input to another cell on the second layer. The output of that becomes an input to the third layer cell. On the right, it's the same thing. I've drawn unrolled for 4 steps. So this is a 3-layer RNN. So the layers going bottom to top, unrolled for 4 steps. So the unrolling going left to right. Okay, there's a few different configurations in which you might find RNNs or architectures. The first one-to-one is basically a feedforward network, so that's not very interesting. Second, one-to-many. This is where you have a single input vector, but the output of the RNN is a sequence. So an example here might be image captioning. So you might have a single vector representing the image, and the RNN outputs a sentence describing the image. The next architecture is many-to-one. Here you have a sequence as input and a single output. So this would be this you could use for classification. Maybe your input is a sequence of words forming a sentence, and your output could be maybe the sentiment, if that sentence is positive or negative or neutral. Next one we get is many-to-many. So here we have an input as a sequence, and the output is also a sequence, but could be of different length. So this we would use in machine translation, for example. Your input might be a sentence in English, and the output might be a sentence in French. And the French sentence may have fewer or more words than the English sentence. Okay? Just one thing to note here is that this cell in the middle, or rather the latent state that connects these two sides of this RNN architecture, actually has quite a lot of responsibility because it needs to capture all the information from the input sequence necessary to construct the output sequence. Okay, we'll come back to that point later. The final one is a many-to-many synchronized architecture. So here we have input sequence, output sequence, and the lengths are the same. So this might be, say you're processing video 1 frame at a time, and you're trying to see, is there a person in each frame? Okay, now let's go to training. So, to train an RNN, we talk, as we do in deep learning, about a forward pass and a backward pass. So the forward pass of an RNN is where we feed our sequence of observations into the RNN and generate all of its outputs. Now what we need to do to optimize the weights in this RNN is we need to see how good the predictions of the RNN were. So to do that, we compare the predictions to some targets using a loss function. Okay? So we're going to talk about the many-to-many synchronized architecture. So we're going to assume we have an input sequence and an output sequence of the same length. So that means we have as many outputs as we have inputs, and our total loss we define to be the sum of the individual losses at each step. So each step has its own target and its own prediction. We use a loss function to compare those targets and to the predictions, and then we sum them all up, and this is our total loss, which we want to minimize. Okay? Now, in order to do backpropagation and gradient descent, we need to compute gradients or derivatives, right? So we need the derivative of our total loss with respect to the weights which we collect in omega, right? So just to simplify notation, I'm not going to use the equation of RNNs that we looked at, which have, the WHX and the WHH and the BH. Just to simplify things, we'll just say HT is a function of the current observation XT, the previous state HT minus 1, and the weights. And the output is a function of the state and the weights. Okay? So let's see now. How do we compute? So the derivative of a sum is the sum of the derivatives. So that's all we've done in the first line, because we said the total loss is just the sum of the step losses. So the total derivative is just the sum of the step derivatives. Okay? Now if we look at this derivative term here, dl d omega, well, we know L is a function of O, and O is a function of omega, right? So now we can apply the chain rule. So the chain rule just says that this derivative is equal to the product of dl do times do d omega. Okay? But now what about this, do d omega? Well, O depends directly on omega, and it depends on H. But H also depends on omega, right? So if we have this situation where we have a function of two inputs, we can just add the contributions of the derivatives from the two parts. Okay, so this is what we do here. So do d omega is dg d omega, so that's just the direct contribution of omega on g, plus the contribution that we get through h. And here we use the chain rule. So O depends on H depends on omega. So we apply the chain rule, and we get this expression. Okay? Now if we just substitute these back, we get this expression on the bottom here. So not too bad, right? But we have a problem. This term here, this derivative, dHt by d omega. Let's look at ht. Well, ht is a function of xt, ht minus 1, and omega. But hang on, ht minus 1 is the function of xt minus 1, ht minus 2, and omega. So we have a problem. ht minus 1 also depends on omega. So we need to apply the chain rule again. Okay, so this term here, dHt d omega, is the derivative of the function with respect to omega, plus applying the chain rule, dHt by dHt minus 1 times dHt minus 1 by d omega. Okay? This is just writing the same thing out, substituting in the function more explicitly. But we get the same thing again, because we have a recurrence relation, right? So this is just going to keep happening. So dHt minus 1 by d omega depends on ht minus 2. So we need to unpack that term as well. So if we do that for a few steps, we get this expression. So don't worry about the details of this. You can look at it afterwards. There's just some things to note about it. Firstly, we have a sum. So if we have a very long sequence, say a year's worth of daily observations, it can become quite slow and quite memory intensive to compute this entire sum. Okay? We also have a product. Now, as you know, if you multiply lots of small numbers together, that multiplication will become very small. If you multiply lots of large numbers together, that multiplication will become extremely large. So if our gradients are small, we get what we call the vanishing gradient problem. As we go further back in time, the gradients get smaller and smaller, eventually going to zero. Or we could get the exploding gradient problem. If our gradients are very large, then as we go back in time, the gradients become larger and larger until they start swinging the parameters off into wild directions. So practically what we do is when we're training RNNs, is we truncate the sequence to some fixed length. So we might say, we're only going to let the gradient go back 10 steps, for example. And then we'll stop it at that point. So this algorithm is called truncated backpropagation through time. So it's the standard backpropagation that you know, but we run it over time, so passing gradients backwards through time, and we truncate it at some fixed point. Okay. But we said earlier that if we know the length of the sequence, we know how many observations are in the sequence, we can unroll the RNN, right? Then we can undo this recurrence relation for a fixed number of steps. So truncated backprop through time is equivalent to running the standard backprop algorithm on an unrolled RNN. So this is pretty cool because it means that your deep learning frameworks like TensorFlow or PyTorch or whatever you use doesn't actually need to implement any special machinery to compute derivatives in RNNs. What it can do is it can just unroll it and then apply the same automatic differentiation that it uses for feedforward or convolutional networks. Okay, so if we look at backprop through time on this unrolled RNN, you'll see we've unrolled it for 3 steps. And we have these gradients that pass from the loss. So the target and the prediction are used to compute the loss. And we have a gradient that represents the DL by DO, which is the term representing like the proportion of error that was caused by the outputs. And more importantly, we have these terms here, these DHT by DHT minus 1 and DHT minus 1 by DHT minus 2. But these are the very important gradients in RNNs, because these terms are what carry information about future losses into the past. So suppose we saw an observation at xt minus 2, and we updated something in our state, which resulted in us making an error in the prediction today. These gradients are the ones that will carry the information backwards to the source of that error so that we can update our weights in such a way that we don't make that error again in the future. Okay, I'm going to skip over these slides. These are just now substituting in the actual equations for RNNs and going through the maths. You can look at that in your own time. Okay, so we were talking about sequences and everything seemed nice, and then we jumped into some slightly complicated looking maths. But the good news is that your favorite deep learning framework hides all of this math under the hood, right? So it's good to know what's going on, but if you just want to build and train an RNN, you don't actually need to know all of that math. So how do we train an RNN practically? Well, suppose we're looking at this example we saw earlier of the noisy sine wave, and we're trying to model the next observation given some history of observations. So suppose we're somewhere here, and we want to say, okay, I've seen all of these observations so far, and I want to predict the next value. Okay? So, like we said, with truncated backprop through time, we need to truncate our sequence to some fixed length. So to do that, we just define how long of a fixed length we want. So here, in the equation, it's tau, but in the code, I've just said it's 5. So I only want to look at the last 5 observations. So now I need to construct some inputs and some targets. So my inputs will just be a sequence of 5 observations, and my target will be the next observation. So that's what we do in this loop here. And most importantly, I guess, is what the data looks like at the end. So our input might be a sequence containing 5 observations, and the target is the next observation. Okay. Now what we can do is we can use, say, Keras, which you've been using in your practicals. We define our input dimension. Our input is just a scalar, so the dimension is 1. Our hidden dimension can be anything, but we just said it's 1 for simplicity here. And our output dimension is 1 because we want to predict a scalar. Okay? So hopefully you should be familiar with this code. You create a Keras sequential, and we add a layer. So Keras includes a simple RNN layer, which implements the RNN equation we were looking at earlier. So we need to tell this simple RNN what size of sequences and inputs it's going to work with. We also need to tell it the size of the hidden state, which they call units for some reason. And because the Keras RNN actually only does the state update equation and not the output equation, we also add this dense layer, which converts that state into an output. Okay? We then compile the model with the mean squared error loss because we're doing regression, and tell it what optimizer we want to use. Adam is just a fancy gradient descent. And then we train the model by passing in our inputs and targets. On the right here, we have the loss curve. So this is just a plot of the mean squared error loss over time. So as our model trains, you can see that this drops and eventually stabilizes at a low value. So we can say that our model has converged. So how good is this model? Well, one qualitative way we could assess how good this model is to generate predictions from the model and inspect. Because we only have one-dimensional data, we can just visually inspect it. So that's what we did here. So the blue plot is the original noisy sine wave. The orange plot is the predictions of the model. And this was generated by seeding some prediction and then asking the model, predict the next value. Then add that to the set of predictions, feed that back into the model, ask it to predict the next value. And we keep doing that. So it's like a bootstrap. We use the predictions of the model, feed it back into the same model, and ask it to predict the next value. So that's what we draw in orange over here. And you'll see that the predictions seem actually very good up to x equals up to 1,000, up to time step 1,000. And once we go outside 1,000, the predictions seem very bad. So this is illustrating a very common problem in machine learning, actually, that interpolation, which is making predictions inside the range of your training data, tends to be much easier than extrapolation, which is making predictions outside of that range. So there's lots of techniques you can use to improve this, like regularization or having more training data, augmenting your training data, lots of things, but that's beyond the scope of today. Okay, so let me just check the times, right? All right. So we talked about truncated backprop through time, and we said that the reason we do this is because we have this vanishing or exploding gradient problem. And RNNs were invented sort of in the 80s, but already by the 90s, people had observed that despite using truncated backprop through time, RNNs were still overweighting the importance of more recent inputs because the gradients were getting smaller as we go backwards in time. And they were having trouble, or therefore were having trouble, tracking long-term dependencies. So a long-term dependency is just the idea that some value you observe now might influence a prediction you make sort of far into the future. So people had found empirically that RNNs had trouble tracking dependencies that went more than just an order of 10 steps. Another problem that RNNs had is that they had trouble ignoring the influence of irrelevant input on the state. So suppose you're processing like a Wikipedia article, and what you're trying to get is the juice of the text in that Wikipedia article. But for whatever reason, you just downloaded the source of the web page, and it's got a whole bunch of HTML tags in it. Now, what you want is your RNN to be able to ignore the HTML tags, because it doesn't contribute to the content of that document. But because the WHX weight parameter, which is what controls the information that enters from the current input into the state, because it's shared across all positions, RNNs will have trouble with this, with ignoring certain irrelevant inputs. So gated RNNs were introduced to alleviate this problem by introducing a memory cell. So a memory cell is basically a piece of storage that these RNNs can use to store some vital information for use in the future. And gating mechanisms are what control what information enters and exits these memory cells. So gating, in particular, gating allows some input to be ignored. So we could say the gate doesn't allow certain input to enter the memory, and it also allows information to be forgotten. So it might allow information to leak out of the memory once it's been used and is no longer needed. So the most popular gated RNN architecture is the so-called long short-term memory. Now, earlier we conveniently introduced RNNs by saying that we have these cells which perform some equations, and they take as input an observation xt and a previous state ht minus 1. And they output an updated state and some output ot. Right? Now with an LSTM, all we do is we decompose the state into two pieces. So one ht tracks just the summary of the past observations, and the other one we call the memory, and we denote it by C. Okay? So we still have the same interface. We have a past state and a current observation, and we output an updated state and an output. So let's starting with this blank slate now of an LSTM cell that has the same interface as a standard RNN. Let's add some components to it. The first component we're going to add is the forget gate. So the forget gate is a gate that controls or that allows the LSTM to drop some contents from its memory. Now the forget gate is controlled by the current input and the previous state. It has its own parameters. So it has two weight matrices, WFX and WFH, and a bias vector. It applies this equation, and this equation should look familiar because it's the same equation we used before in an RNN. And it applies a nonlinear activation. But this time, the activation function is the sigmoid function. And the reason being that the sigmoid function squashes values to lie between 0 and 1. So now, if we take our previous memory contents and multiply it by the forget gate, which is a value between 0 and 1, then if this forget gate value was 0, we would essentially drop the contents of the memory. If the forget gate value was 1, then we would remember the contents of the memory. The next component we add is the input gate. So the input gate, it looks exactly the same as the output gate, but it has its own parameters. It's a value between 0 and 1, which depend on the current input and the previous state. The value of the input gate we use to multiply by the tan h applied to the current input and previous state. Now the reason we do this is because tan h squashes values to lie between -1 and 1. And if we're having information potentially entering our memory, we want to make sure that every time information enters, it's on the same scale as what's already in the memory. Because if the scale were wildly different, say if your inputs just happen to be very large at a particular time step, even though the input gate might be trying to say, no, I don't really want this information in memory, just the fact that the input has a very large scale might lead it to dominating the memory anyway. So we use this tan H to make sure that everything's on the same scale. Okay, the final component is the output gate. So the output gate controls what information gets read out of memory and becomes part of the current output and the next state. So, again, exactly the same equation, but the output gate has its own parameters. We apply a tan H to the memory and multiply it by the output gate, and that gives us the next state. Okay, so these are the equations, just all grouped together. So we have 3 gates. Each gate has 2 weight matrices and a bias vector as parameters. We have some more, I guess, standard RNN parameters, which control, which basically create what we call a candidate state by multiplying the current input and the previous state. We apply a tan H and we multiply that by the input gate to control how much information we want to enter the memory. And we add that to the forget gate times the previous memory contents. So this is the equation that controls how we update memory in the LSTM. And then finally we have the output gate multiplied by the tan H of the current memory becomes the output. Okay, so we said initially that these gated RNNs were introduced to alleviate the vanishing gradient problem. So how do they do this? Like, it's not really obvious from these equations how we are getting around the vanishing gradient problem. Well, if we think about it, suppose the LSTM learned parameters such that in certain cases, the forget gate was set close to 1 and the input gate was set close to 0. Well, let's look at these equations and see what happens. If the forget gate was 1 and the input gate was 0, this term vanishes, and we basically say that the memory is just a copy of the previous memory. Now, if you were calculating derivatives, if you were calculating dct by dct minus 1, that derivative is just 1. So what happens is, the LSTM has the ability to essentially switch off certain cells. So if the input is not relevant at a particular time step, it could basically create an uninterrupted flow of gradient through that cell, effectively ignoring it. And so this is how the LSTM can learn to allow gradients to propagate quite far back without vanishing. So LSTMs have actually proved to be extremely popular, very effective. They're used in lots and lots of real-world products. And they've even proved to be very hard baselines to beat. Like one interesting work in particular was some work by some DeepMind colleagues where they compared a well-tuned LSTM to some more recent, very fancy recurrent neural network architectures, like recurrent highway networks and even neural architecture search. And they found actually that if you just tune an LSTM's hyperparameters well, that it outperformed those much fancier and much newer models. So LSTMs are a very, very good starting point, a good baseline. Okay, the next gated unit we'll talk about is the gated recurrent unit. So this is similar to the LSTM in the sense that it's a gated architecture, but it's newer than the LSTM, and it has fewer parameters. So remember, LSTMs have parameters, 2 weight matrices, and a bias vector for 3 gates, and it's got the weights and the bias vector that you see in a normal RNN for the candidate state. So gated recurrent units, by reducing the number of gates, reduce the number of parameters required. Empirical evidence suggests that these gated recurrent units in many situations perform just as well as LSTMs. So we'll start again with the blank slate of having an input and a previous state as inputs to our cell. And our cell has an output, which is the updated state. First component we add to construct a GRU is the so-called reset gate. So if we look at a state update equation, so normally we have this activation function of some multiplication of the input plus a multiplication of the previous state plus a bias. The most obvious way you could reduce the influence of the previous state on your new state is to just add some number here which multiplies the previous state by a value between 0 and 1. And this is exactly what the reset gate does. So this equation is the same as what we've seen before, but we've just added this reset gate in here. And the reset gate is computed in the same way as we do with LSTM gates. It's based on the value of the current input and the previous state, and we apply a sigmoid so that the value lies between 0 and 1. Okay, so in a diagram, it looks a bit messier than a LSTM, but the equations are hopefully fairly self-explanatory. So we use the input previous state to compute reset gate, which we multiply the previous state with. We apply a tan H, and we call this a candidate state because we're going to do some more processing. Okay, the next component, so GRUs only have 2 gates, right? So we already got 1. So the next gate is the update gate. So the update gate leads to basically creates a convex combination of the previous state and the current candidate state. So we say that so we compute the update gate, again, just like we compute every other gate. We call it Z, has its own parameters. And now to compute the output state of the GRU cell, we take the value of the update gate multiplied by the previous state plus 1 minus the update gate times the candidate state. So here's the candidate state, here's the update gate. We multiply the previous state by the update gate, and we add it to 1 minus the update gate times the candidate state, right? So now, what does this update gate do? Well, imagine the update gate was set to a value of 1. So, if that were the case, then what we're effectively saying is that the current state, or the updated state, is just a copy of the previous state. And the derivative, dht by dht minus 1, would just be 1. So now we've achieved the same thing that the LSTM did with its 2 gates. We've created basically a bypass-like connection through the GRU cell that allows gradients to flow through it and ignore the current inputs. If the update gate were 0, then our new state would basically be the candidate state, and the candidate state could still incorporate information from the previous state depending on the reset gate. So that loop's a bit more complicated, but the important one is if the update gate is 1, then the GRU cell allows gradients to pass through it uninterrupted. So here's the equations just collected all together. I won't go through that. Again, some more good news for you, though, is if you're using TensorFlow or Keras or PyTorch or whatever, because these gated cells conform to the same interface as the simple RNN cell that we introduced earlier, using them is literally as simple as taking the exact same code we had before and change the word simple RNN to LSTM, and now this will work. So these frameworks make it really, really simple to experiment with these standard architectures. Okay, very, very quickly some examples. So one very common application of gated recurrent neural networks is in language modeling. So you'll see in the practical later this afternoon that you're going to be asked to take some Shakespeare text, chop it up into characters, and train an RNN with it. Then we'll use the predictive model to generate some new text that hopefully will be in the same style as the Shakespeare text we trained our model on. So this text here was actually generated by an RNN. This is not a real Shakespeare play, but it looks pretty realistic, right? Another interesting example that's on Andrej Karpathy's blog is he took the Linux kernel source code and he trained an RNN with it, and then he asked the RNN to generate some new code. And this is what an example of something it generated. So it's C++, so it looks maybe a bit cryptic, but it seems to get the structure right. Like it knows words like static, int, it opens and closes brackets, it seems to know the structure of an if statement, it knows how to make comments. Like it looks pretty good, right? It looks pretty realistic, like you could think a human wrote this. And when they analyzed, this was a deep RNN, and when they analyzed like the activations of cells in that stack of RNN, they found like quite a few interesting and very interpretable results. So one interesting example that they found was that certain cells would activate sort of when you were inside an if statement. So those cells might be tracking, for example, or other cells might be tracking when you've opened a bracket and remember in the memory cell of the LSTM that at some point I need to close it, and once you've closed it, the memory gets forgotten. So the LSTM is kind of doing exactly what it was designed to do there. Okay, another interesting example, very real-world example. I'm sure a number of people use Android phones, and on an Android phone, the default keyboard is called Gboard. So Gboard is full of LSTMs, like all over the place. So with Gboard, you can scribble like with a stylus with your finger, and it'll convert your scribbles into text. And it uses an LSTM to do that. You can also do like swipe typing, where you just like don't lift your finger and swipe across the letters. Again, it uses LSTMs to decipher what you were trying to type. It even uses it to convert on-device speech into text. Okay, so, sorry Rosemary, how much time do you have? 20 minutes, okay. Since we have time, I'll briefly talk about attention. So, the setting that motivated the introduction of attention is many-to-many sequence modeling, also called encoder-decoder architectures. So this is used in machine translation quite extensively. So we have an RNN that processes a sequence of words, say, in one language. So for example, this could be 4 words in English. It creates a representation of that sequence of 4 words, which we call a context vector. The context vector is really just the last latent state of the input RNN. So we just record the last latent state, we call that a context. We feed that as the initial state into a decoder RNN. Now the decoder RNN is basically just generating a new sentence, say in a different language, say in French. Now, hopefully you can see that this seems potentially problematic, because this poor context vector has to remember all of the relevant information in a potentially very long sequence that's necessary to capture the entire meaning of that sentence, such that a sentence can be generated in French which captures that meaning. So this poor context vector's got quite a heavy weight on its shoulders. So this motivated the idea of introducing attention. So attention was designed to free the encoder-decoder architecture, or free this context vector from having to remember all of the relevant information from the input sentence, or sequence rather. So what we do is we say that while we're processing our input sequence in the encoder, we're going to generate intermediate outputs and save them. Okay. Now when we get to the decoder, at the first step in the decoder, what we do is we allow that decoder cell to refer back to the encoder outputs. Okay. So, and use those encoder outputs to construct a custom context vector for that particular position in the decoder. So at the first decoder cell, for example, it'll use an attention mechanism to refer back to the encoder outputs, generate its own context vector, and use that along with the previous latent state to generate its output. The next decoder position repeats this process. So it'll run the attention mechanism again, referring back to the encoder outputs, and use that along with the previous state to generate another output. And we keep doing that. So what happens in this attention computation? So essentially what these decoder cells are doing is they're using the previous latent state, ht-1, to compute an alignment score with each of the encoder outputs. So all an alignment score means is that it's trying to compute a score that measures how relevant the encoder output is to the particular position that the decoder is in. So it does that using this slightly complicated looking function. Basically, in this particular form of attention, which I believe was the original one that was introduced, they would take the current latent state, ht-1, along with the encoder output at position I. So this might be, for example, the first encoder output, concatenate them together, multiply it by a parameter matrix, and take a nonlinear activation function, and then multiply it by another parameter vector so that we get a scalar number. Yeah, so don't worry too much about that. Basically, the score is just a scalar number that measures how well the encoder output at position I matches, in some sense, the decoder position T. Okay? So now we generate these scores for each of the encoder outputs. So we repeat that equation for O1, O2, O3, and O4. Then we apply a softmax function. So a softmax function, this is just the equation of a softmax function. Basically, a softmax function normalizes a set of numbers such that they sum to 1. So for each of these encoder positions I, we get a number that lies between 0 and 1. And if we add all of them up, we add all the attention weights, which we now call them. If we add them all up, we get 1. Okay, so these are the attention weights. Then we multiply each encoder output by its attention weight and add those all together. And this is how we construct this context vector, CT. So you'll see, basically through this score, the context vector CT changes depending on what the decoder is doing. And what the decoder is doing is determined by the state that feeds into the decoder at that time step. So cool thing about attention is that you can visualize these weights. So for example, say you're doing some machine translation. Here I think it was translating a French sentence into English. At each step, you generate these attention weights, and they all sum to 1, so you can think about it as a probability distribution. Now you can stack these all together into a matrix and create this cool visualization. This kind of shows that, okay, when we were at the 5th position in our decoder, the attention mechanism was looking at this position in the encoder. So that's the, 7th position in the encoder. And I don't speak French, but that looks like the French version of European to me. So that seems to make a lot of sense, right? So what these attention mechanisms are doing is a sort of automatic alignment. So alignment was actually a very difficult problem to do originally in NLP. People came up with all sorts of techniques for doing it. Alignment is basically the problem of matching which word in an input sequence is relevant for the corresponding word in the output sequence. And attention does that automatically. So there's lots more to talk about with attention, which we don't have time for. In particular, there's all kinds of different score functions. So the score function we looked at was the additive score, which was the original one. But there's lots of other ones, like you could use cosine similarity, you could only look at the location, perhaps, rather than the contents of the vectors. You could do a dot product attention, scale dot product attention, a few more variations. Then another interesting one is, so attention was originally introduced in these encoder-decoder architectures, where we basically had one RNN that was attending to all of the outputs in another RNN. But suppose we just throw away the second RNN, and we currently at the fourth step in a single RNN, we could use an attention mechanism to refer back to the outputs of the last three steps. And that's called self-attention. So that's just a sequence that attends to its own history. And self-attention is actually such a powerful thing that in the paper, Attention is All You Need from Google Brain, they discovered that, hey, we actually don't need all of this RNN stuff. We can just take these self-attention mechanisms, run it on the entire sequence, and get state-of-the-art results in machine translation. And there's been tons more work now on this. Transformer architectures, variations of them, and also further developments of attention mechanisms into sort of full-blown like memory architectures. Like the neural Turing machine from DeepMind was basically operated kind of like a computer. It has like a bank of memory, and it can write values into the memory and read values out of it, and it does all of that using attention mechanisms. Okay, so an example of attention mechanisms that are used in products that you use probably fairly regularly. The production Google Translate system actually uses LSTM encoder-decoder architecture, so with an attention mechanism. And it's exactly the same attention mechanism we just talked about. And it's the same LSTM cells we just talked about. And this is powering like a Google scale product, right? The only real differences between what we talked about today and this particular architecture, so firstly, it's a stack. The encoder and the decoder each have 8 layers of RNN. But they, in the encoder, also do what they call bidirectional LSTMs. So what this means is that one LSTM sort of processes the sequence left to right, and another one processes the sequence right to left. And then the representation for each word is just the sum of the left representation and the right representation. So this just allows them to incorporate information from both sides of the sequence when they're trying to represent a particular word, say in the middle. The other difference is that they have skip connections or residual connections. So basically what these things are is that they allow us to have fairly deep architectures, but which give the model more capacity, but also allow the model to skip over some of those layers to allow better flow of gradients. So it kind of gives the model more flexibility. It can use the capacity if it wants to, or it can skip and allow it basically to, the skip connections kind of allow you to have a model class that captures like an 8-layer, 7-layer, 6-layer, 5-layer, 3-layer, etc., by allowing it to switch off layers if it doesn't need them. Okay, so yeah, that's Google Translate. So it's using the same stuff we learned about today. Other interesting thing about this is that it actually operates on, I think, over 100 language pairs simultaneously. But yeah, technically you can fire up TensorFlow and Keras and build yourself a Google Translate system. Okay, so in summary, today we talked about sequences and how to model them using autoregressive modeling with fixed context length and with latent state variables. We tried applying feed-forward networks to them and saw some limitations. which motivated the introduction of recurrent neural networks. We talked about unrolling RNNs through time. We talked about stacking them to form deep RNNs. We talked about a few variations on architectures. We talked about how you can train an RNN using truncated backprop through time. And we found that there were still some issues with vanilla RNNs related to vanishing gradients. And that motivated the introduction of gated networks, which are the LSTM and GRU. And then finally, we talked very briefly about attention and how cool it is. So thank you, everyone, for your attention. And yeah, that's the end of my talk.
As stated, the introduction of the gated network, LSTM, does it mean there are no limitations with the LSTM? Because we've seen work where someone introduced regularization dropouts. And also, the second question I was about asking you, towards the end, you delve into it. These days, technology is going beyond ordinary LSTM to gated, deep directional LSTM. Is there no drawbacks that led to that? Or what could have made technology to move from ordinary standard LSTM to deep bi-directed LSTM? Thank you.
Sure. So, okay, so with the bidirectional LSTM in particular, you'd find those often in encoders, because an encoder is trying to generate an output at each position, right? But if you just process the sentence left to right, then if you're currently at the middle word, you would only have information from words that occurred before it in the sentence. But there might be words that occur after it in the sentence that are also relevant. And so the bidirectional LSTM was introduced to combine information coming from both sides of the sentence into the representation of the word in the middle, say. Okay? So that they found, that's very useful when you don't have like a causal modeling problem. So you have the entire sentence that you want to encode. You have all the words already. So it's fair to combine information from the entire sentence into the representation of the word. Whereas in the decoder, you're generating one word at a time. So you can't look into the future because it doesn't exist yet, right? So limitations, the limitations are actually the same as with standard RNNs. So the LSTM improved it, but it didn't solve the problem of vanishing gradients and long-term dependencies. So LSTMs maybe took the dependency length, say, from 10 to 30 or so. But if you have much longer dependencies, LSTMs still struggle with them. And that's where you see lots of the variation in LSTM architectures coming from. Although people have found empirically that a lot of those variations, it's actually very difficult to beat the standard LSTM. And more work is coming out that's showing this. But people have come up with all sorts of crazy ideas on variations. Yeah.
Yeah, thanks so much for the talk. That was super informative. I went from sort of mystified about a lot of these things to understanding a lot more than I think I did before. So my question is about, I guess it's a practical concern with language modeling. So with languages that are very agglutinative, like let's say the English word disincentivization, how do you, just in practical terms, break those into units in a sort of like principled way and then recombine them into units? So like some languages, like a single word might encode the context of an entire English sentence. How do you go about actually representing that?
Yeah, so that I guess is more of an NLP question, which I'm not much of an expert in. But I know there are techniques in NLP for sort of breaking up words into parts. I'm not too familiar actually with how that actually works, but I know there are techniques for dealing with that. So instead of modeling like characters or entire words, you would come up with some kind of splitting scheme and model parts of words as your tokens in your vocabulary.
I understand that stacked LSTM were introduced to bring in an element of deep learning in LSTMs. Mm-hmm. How deep can it go? How many layers can we stack, and what's the limitation to that?
Yeah, so it kind of depends. Like technically, you could build very deep LSTMs if you want to, maybe 32 layers or more, but you'll find you kind of have the same problem of vanishing gradients, but now operating down your stack. So if you make an error, so the output of your LSTM stack comes from the last layer, and suppose that error were introduced in the first layer. Now that gradient needs to flow through 32 layers to get to the source of the error, right? So again, you have the same problem. You multiply gradients and it can vanish. So this vanishing gradient problem applies in deep networks as much as it does across time. So, so this motivated, for example, introduction of techniques like skip connections and residual connections, because it's kind of like the same idea with an LSTM, where it allows channels for gradients to sort of skip over layers. But it's really it's the problem of propagating gradients that will constrain how deep you can go. And there's lots of modern techniques for dealing with it, but practically, like, I guess I haven't really seen many LSTMs deeper than like 8 layers. So even the production Google Translate system, like they have a lot of resources, right? But they're running only 8 layers in their LSTMs.
Examples of types of RNN is many to one network, of which a typical example is in sentiment analysis. Now, for instance, I'm using LSTM, but I want to know if I want to classify a sentence both into the opinion, the sentiment, and at the same time an aspect of that sentence. Can I also use LSTM for this? Is it suitable?
What do you mean by aspect of the sentence?
For instance, let me go deeper. Sentiment analysis has sentence level. You take a sentence and then you classify whether it's negative, neutral, or positive. And then you also want to go further to know what feature of this sentence are we talking about. For instance, talking about phone, maybe the battery, maybe the charger, maybe the other software feature. I want to know if LSTM can also be used to classify that aspect.
Okay.
Of the
Yeah. So there's various options you could do there. So yeah, LSTMs would be suitable. You could, for example, use synchronized many-to-many and sort of classify the sentiment of each word independently, and then combine all of those into a final sentiment of the sentence. So that's one option. Another option you could do is maybe use self-attention and see sort of the attention weights given to the words for the final classification. So maybe it might say, okay, there's the word sucks in the sentence, and that gets a lot of weight from the attention mechanism. That might suggest to you that that word is what is driving a lot of the resulting classification. And other words maybe have low attention weights, so they're not very relevant, like phone might not be relevant for sentence classification, sentiment classification rather. You could also do things like break up your sentences into subparts and run LSTMs on those subparts. There's a few options you could do, yeah.